Okay, so we'll get started. Towards the end of the last class, I realized that some of the content is probably very, very new to you. So I wanted to slow down a bit, go back, make sure everybody is on the same page before we proceed. It's also not the most easiest content to grasp if you have not seen this earlier in your life, right? So I wanted to slow down because I realized towards the end of the last lecture that there were certain places where I might have created more confusion than to help you. So we'll do some quick exercises, and hopefully the goal today here is that at the end of today's class, everything about hypothesis testing should be clear. Anybody who gives you data later on in life, you'll be able to figure out what is your hypothesis, what you're really testing, and some tools to test it, right? So what we tried to do in yesterday class and today's class is a subject in itself, right? This is the subject of hypothesis testing. If you take a class in statistics, or if you take a course in statistics, this full thing can be a full-fledged course in itself. So we'll not be able to do that. We'll not be able to do justice to it. We'll try to get as close as we can to be able to summarize what we can get, so that we have enough information, we are ready, we have the tools to process data, to make insights as much as we can with respect to the health data. Okay. So I wanted to start with an area which is not my expertise, and you'll see what that area is in just a bit. But we live in a modern world where I can use some help, and this is the area of poetry. So this area, we'll talk about where exactly it comes from. So this poem is on statistics and what we did in the last class. So in a land of stats, so wild and vast, hypothesis testing has made students aghast. Is it null? Is it not? Should we reject? Confusion spread, which is hard to correct. Then came the voice. Here's the key. State your null as plain as can be. Assume it's true. Don't let it stray. And let your data have its say. But oh, the p-values. They played their tricks. Below 0.05, is it a statistical fix? Above that line, we must comply. The null survives, let the data fly. Okay? So this is partly in collaboration with ChatGPT, right? So this is an area which is totally out of my expertise, but we can use some help, right? We can use some help to come up with this, right? So this is an area which has been confusing for years, right? So does everyone here follow XKCD? Or it used to be a thing like maybe 5-10 years back. This is a web comic. I think that era is slowly fading away. This is a famous comic which says that, in school, this is technically the definition of school, we are still teaching about null hypothesis. I remember reading a big study that conclusively disproved a null hypothesis. Right? So hopefully, if you spend some time, you'll get the joke. And the goal here is to sort of help you figure out what the joke is here in just a bit. So we'll review the chi-square test and the G test. We'll do some very quick. This is nuts and bolts for something that's coming up. So we'll quickly go over what is expectation, what is variance, what is central limit theorem, what is normal approximation. And then we'll talk about testing for difference of means. So I want to really get to it, and hopefully we can get there. And if there is time permitting, I will start talking about discussion, just a very quick primer of what is dimensionality reduction, right? So if you remember the first lecture where I give you or for the first or the second lecture where I gave you the preview of what is coming in the class, we are still in between the first vignette, which is we are still testing for what is the model. We are still in the hypothesis testing stage. We'll now make a transition. We'll go into the dimensionality reduction. Right? So this is a quick, hopefully today's lecture will be a quick turnaround point for also getting you started with the assignment. So it should be out later today or tomorrow. I added you all on Gradescope. Gradescope is a website for where you'll be submitting your assignments. You must have gotten an email. Just check it. The assignment is not out yet, right? So you just have been added there. You'll get a notification once the assignment is out. Okay. Any questions? So there was one point of confusion. We spent like half an hour after the class last time with some students talking about why do we what is so special about the way we select the null, right? And I did not emphasize it enough in the last class about like why we choose certain choices. One of the choices that we made was we were trying to compare the null in our case. The example that we took was the distribution of deaths in 2015 to 2019 is similar to the deaths distribution in 2019 to 2023, right? Why that? Why not like it's different? Why not start with that null? So we'll just very quickly discuss what is the reason for that, right? So the purpose of hypothesis testing is to largely is to do some sort of self skepticism, right? You want to be really conservative, right? So the conservative approach in any scenario is you assume if you're given any two observations that they probably came from the same setting, right? So that's the premise which we take when we formulate a null hypothesis. And you'll see in just a bit why it's easy to sometimes formulate this rather than make a complicated null hypothesis, that maybe one population is greater, maybe one population is different. This is very similar to what is followed in the judiciary as well, which is you're innocent unless you're proven guilty, right? So your population, the observations that you're seeing, your null is they came from the same set. They came from the same population. The distribution is similar. Their mean is similar. Any sort of comparison, you assume the simplest idea, which is that things are very similar, right? So this is what's called the Occam's razor approach. There are different interpretations of Occam's razor, but it is the simplest idea there is you assume you do a minimal assumption in any of the analysis that you're doing, and the null hypothesis is basically a version of that. So this also comes from this falsification paradigm, and this is a philosophy in itself. So Karl Popper was a philosopher, and one of the things that he said that we cannot conclusively affirm a hypothesis, and I'll give you an example of what exactly that means in just a bit. But we can conclusively negate it, right? That's the premise of null hypothesis. It's very hard to conclusively say something is true, but it is easier to say something is probably not true. Okay, we'll see an example of that in just a bit. So if you're formulating a null hypothesis, the first assumption that you make is things are similar, right? The reason you formulate this particular hypothesis is because it is easier to find evidence against it. And why is that? Because whenever we are making any sort of inferences, we are talking about, is there a difference between population, right? Our focus is, if I'm talking about deaths, I'm talking about how does the number of deaths differ between two set of years, right? So, but what I'm trying to do is, I'm trying to make, I will not be able to measure all the deaths in India, right? All you will be getting is some sample of deaths. It's very hard to measure each and every death that happens. It's also hard to even assign them a cause. So I cannot say that the trauma related deaths, I've been able to measure all of them at once. You will always get what's called a sample of the population. So the number of deaths that happen, that becomes your population. What data we have is a sample of that population. And ideally, our goal is to compare the population differences, right? The population of people who, the population comprising of the deaths that happened between 2015 to 2019 and 2019 to 2023. Very, very hard experiment to do, right? There is no way you will be able to measure each and every individual who dies because of trauma. Okay? Even just because of one cause. It's very, very hard to track each and every one of them. So what we do is we do some sort of sampling, right? So what version of the data that you saw was a sample data, in the sense that it does not represent deaths across India. It's a relative representation that if I have 36 states, I can take 5 units or 5 sample hospitals there and just track them over time. And I believe that they will reflect what is happening in the rest of the country. That's the assumption that the data is based on. Okay. So if you take an example that if I gave you this hypothesis, that is there, whatever population you're seeing. So let's say I take height or BMI index of this class, and if I take the BMI index of the class which is next door, LH102, right? And I wanted to understand, is there a difference between the people, the BMI of the people sitting here versus the BMI of people sitting there, right? So this is a sample version. My goal is to compare, for example, if this class was, let's say, of all chemical engineering people, and the second class was of all electrical engineering people. I want to figure out what is the difference between these two populations. So in this case, measuring each and every person is relatively easy. I could do that. But let's say I want to say that, okay, I don't want to do that exercise. Let me do a simpler exercise, is sample some of you and then sample some of the people there, maybe 10 people. There are whatever, right now there are 80 plus people sitting in this class. I don't want to waste time doing 80 samples. I will do just 10 samples from here, 10 samples from there. All the conclusion that I draw will be drawn on that sample, right? So if I want to compare and say that there is a mean difference between the two population, the population here comprising of entire chemical engineers in this class and entire chemical engineers in that class, assume, or electrical engineers in the other class, the inference will be based on the sample that I draw. And the conclusion that I will have to draw is the question that I'm asking, is there mean difference between the two populations, right? So this requires, it's easy to say rather than, there is the null hypothesis in this case that I would like to start with is that there is no mean difference. There is no difference in the mean BMI of this class versus the other. The reason it's a simple hypothesis is because if I say that they are actually different to begin with, I have to also define what that difference will be. That gap could be like 1, the gap could be 5, the gap could be 15. The moment I start to think about that, it becomes very hard to really test it, right? There is no way to sort of figure out what that gap is before you get started. You can come back to it once you have defined, once you have sampled certain people, you can come back to it and you can, refine it and so on. But the simplest approach is to say that there is no difference. That's what we take. Okay. So think about an argument. Think about, I'm making a claim that all swans in the world, or all swans that you find anywhere in India or wherever, right? Doesn't matter what the location is. Let's take all the world. It's white. What is easier? Is it easier to test? Is it easier to accept this hypothesis, or is it easier to reject this hypothesis? Reject. Why? You only need to find one non-white swan and you can reject it. If I have to really claim that this is accept, I will have to first do a sample, but that sample will not, you'll not be able to do like there's no way in this world that you can capture all white swans. So it's very easy to reject it. All you need to do is look for one black swan. So your hypothesis testing framework that we talk about tries to look for that one black swan. Okay? That's why we formulate the most simplest hypothesis. That's our null hypothesis. Is that concept clear? Any questions about null hypothesis? Okay. So we talked about p-values. This is just a revision, right? So the p-value, this curve again that you're seeing, it's very important to figure out, or it's very important to appreciate that this curve is the distribution of the test statistic. What is a test statistic? So it's a quantity that you measure, which will help you summarize your null hypothesis. Okay, so we'll see an example of the null hypothesis in just a bit. But when we started with the death example, the null hypothesis there was that if you look at the distribution of the deaths, The distribution was defined based on categories, which is the histogram that we created. In total, we were tracking 48 months worth of data. We binned them. So we binned the deaths into different categories: death between 3,000 and 4,000, between 4,000 and 5,000, 5,000 and 6,000, and how many deaths happened. So we were tracking that as our distribution. And the question that we were asking is, if you look at these two different distributions, whatever that kind of shape is, are these different? And the claim that we started with, the null, was that this distribution is similar. So I realized that I started with a very complicated null, or a very complicated example. I think the null is fine. The example is slightly complicated. So we'll try to refine it and make sure that we all understand. Okay. So what we're trying to do here is, once you formulate this kind of a hypothesis, you'll have to come up with a way to quantify the difference, right? So in this way, the way we came up with that quantity was, we said that if we track these bins, so let's say this is bin 1, bin 2, bin 3, bin 1, bin 2, bin 3. I'm going to say that this is my previous year ka data, right? So this becomes your expectation number. This is your number of values that you expect. So this is E1, this is E2, this is E3, this is O1, O2, O3. So I had some expectation. I made certain observations. Now I need a way to be able to quantify the difference. And the way we quantify this was with a chi-square statistic, right? So this will go from I equal to 1 to 3. This is it doesn't end here. You have just been able to quantify this. What you're saying is this distribution is similar or the same. That becomes your null. So your null is, and this is a complicated null. I'll just call this A and B. Okay. So once you've come up with your test statistic, you say that this statistic, I'm saying that it's going to be distributed with chi-square, right? So there are 3 entries. So the degrees of freedom will be 3 minus 2. There's nothing special about chi-square. Every hypothesis testing that you do does not mean that it will end up with a chi-square. The reason in this case it ends up with a chi-square is because we are testing for difference of distributions where there are certain categories which are predefined. So I did not make this point clear, and I'm sorry about that. I think that created a lot of confusion. So the categories in this case are your 1, 2, 3, which is basically the number of deaths that happen. So in this case, you'll see this on the slide. This is 3,000 to 4,000. This is 4,000 to 5,000, 5,000 to 6,000. Those are the examples. This chi-square statistic that you derive is a special sort of requirement or special case that you get if you're testing for differences in distributions of these categories. What we said is, this is your chi-square. Okay, this is your chi-square with 2 degrees of freedom. This holds only if, this is the important part, right? So the reason this distribution should look like is when H naught is true. So that is the key. That is one thing that you should remember, that this only holds if H naught is true, if the null hypothesis is true. Okay, so we got some value. We defined a threshold value of alpha, right? So this is some x square alpha or x square alpha, just to make sure there is a distinction between the degrees of freedom. This area is alpha, right? And the alpha value that we set generally is 0.05. This is arbitrary. It could be anything. It could be 0.01. It could be 0.0001. It just tells you how much liberating or how much liberal you want to be to allow for higher type 1 error. Okay? The more you go here, you will start to reject your null hypothesis more and more, but that also increases your type 1 error, okay, because this is the region of your type 1 error. Then what we did is we found out, once we calculate this statistic, let's call this z. Where does the z lie? So if z lies here, what this then tells me is the probability of observing something which is as extreme as z, right? That's the question that you're asking. What is the probability that I can see something as extreme as z? So I'm tracking this area. And this area happens to be bigger than your area that you had predetermined to be the area of rejection. So if this area is ZA, we found ZA, if we find this to be greater than 0.05, there's nothing very surprising about this, right? What this essentially means is, if the null is true, then I will see this value with a very high probability. So I will fail to reject. I will fail to reject my H0 because there's nothing surprising about this. Had the same scenario been in this small region, which is beyond alpha, if I had found my Z to be here, let's call this ZB. So this area becomes very, very small. Since ZB is less than 0.05, what I'm going to make a claim now is maybe H0 is true, but the value of seeing something as extreme as ZB is very, very small. It's smaller than the threshold that I've already defined, which essentially means that maybe the null does not hold true. Okay, very loosely, that's what it means, because this curve that you're getting because you assume that H0 is true. Okay, does this make sense? Any questions? Yes. Yeah, that's definitely a possibility. You have to decide which test is appropriate for your setting, and we'll see an example of what those tests are, right? So the choice of test comes from what you know about the data, right? So that is one thing which I really missed last time. So I think that's the key, right? So in this case, the reason we are using a chi-square test is because it's a test for goodness of fit. The reason we are checking for goodness of fit is because we had a prior expectation of checking whether the deaths that happen in these bin categories, 3000 to 4000, 4000 to 5000, 5000 to 6000, is that remaining similar between the two 4-year populations, or the two 4-year whatever trends. Okay, any doubts, any questions, any concerns? This one. So yes, that is an underlying assumption that the OI minus EI is assumed to be following a standard normal distribution. We usually don't check for it, and it's a very forgiving assumption that you make, but that's the assumption that you rely on. That OI minus EI is approximately standard normally distributed. Okay, that's a very good point. Does that make sense? So there's an implicit assumption that these values are approximately normal, and we'll see how to check for the normality. So you can check all of this in a while. It's sufficient, but not a required condition. It's not required for running chi-square test that this has to be normal. Okay, slightly technical. For all practical reasons, if these values If this value that you're checking, you can check for the OI minus EI differences, and if they are approximately normal, you should be able to run it. If not, also the p-value that you get is not grossly incorrect. Okay, it's very, very close to some other ways of being able to test this. Any other questions before we proceed? Okay, so this is again a revision of last time. So type 1 error is the probability that you end up observing or you end up rejecting the null even though the null is true, which is very simply this region, right? Because we know that we made that choice. We are okay living with that choice that if h0 is true and still my z belongs or chi-square belongs in this region, I'm going to reject it just because this is a very small value. And because of that fact, I'm going to make a type 1 error. Okay. There's another scenario possible, and I drew this is h0, right, which is the distribution of under the null. It's very hard to come up with an alternative. It's how the alternate distribution would look like. It's hard to draw. I don't know if I should draw this. I don't know if I should draw this, or I don't know if I should draw this. I don't know the alternative, right? I don't also care about what the alternative is. Because my null to begin with was very, very generic, which is the distributions are similar or not. What I took the example of was, I said, let's take a simplistic scenario. Let's take a simplistic scenario where my null is this. This is also, there is no way to figure this out, what is true and what is false, right? Unless you do a simulation, you cannot figure out what is true and what is false. Nobody can figure out what is true or false. All you can do is like make a statistical estimation. What I said then is, okay, let's assume that this is the curve that you would have gotten if your alternate hypothesis was true. You don't know this. There's no way you can know this unless you do a simulation. And then if this is the region that you will do a type 1 error because you reject then in the same scenario with this is your threshold. If I look into this region, if my h1 is true, so which means my h0 is false, this region, what is this region? What is happening in this region? So h1 is true. We know this is false. Okay, so this falls in the non-rejection region, right? Again, you're not going to be able to observe this. This is a theoretical scenario. Okay, what is this then? Why is it a type 2 error? What is happening here? Or fail to reject. Accept is not the right word. Fail to reject. The reason we choose fail to reject versus accept is because if you have to prove something, you need to gather all possible evidence in this world. But you're working in the sample world where we cannot measure all of the things, right? So maybe it's there, maybe it's not there. We don't have enough evidence to reject it. That's why we say fail to reject rather than accept. For requiring to say something like accept, you would have to go back and measure all the swarms in this world, right? So think about that. That's why we say fail to reject. Terminology is clear? Type 1, type 2 error is clear? Okay. Okay, in that case, I will proceed. So what is p-value? What is p-value? Very quickly. Yeah. It is in the rejection zone. Okay. Anyone else? Good. So it's not the probability that is in the rejection zone. Okay. What is p-value? It's nothing special actually, right? What it is I can define it to be this region. What is the probability that I will observe something as extreme as whatever you're observing? Whatever is your chi-squared statistic, what is the value, what is the region, what is the probability that you'll observe something as extreme? And all this while I've been drawing it on the right side, that there's no reason for that. Depending on how you want it to be, you can also say that the other side is also extreme, right? So if it is a normal, if you we'll do an example of this in when we start talking about difference in the means. So for example, if you have population P1 and population P2 or sample, actually, yeah, fine, it doesn't matter for now. If my null hypothesis is the sample is equal, the alternate hypothesis is that this is not equal, which means it can go, if I take the difference of mu1 minus mu2, it can either be positive or it can either be negative. So in such scenarios, I would also be interested in asking that whatever test statistic, you have not seen what that test statistic is if you want to test for this, but assume there is a black box test statistic. The question that you'll ask is this value, whatever way you measure it, you quantify it, is it as extreme? So this extreme could be positive, this extreme could also be negative. Okay. So in most cases, I'm just highlighting the right part. All I want you to understand is p-value is just the probability under the null, assuming the null hypothesis is true. What is the probability that you will see something as extreme as your test statistic? The test statistic changes based on what test you're doing, what assumptions you're applying. Okay. Any questions? Any questions? Following questions? Is that clear now? So it's not the probability of testing of the alternate hypothesis being correct. It's not the probability of observing the result by chance. It's the probability of observing a result which is as extreme as what you're observing. Okay, so this I should bold. If the null hypothesis is true. Okay. So we did an example of this chi-square test, right? So the chi-square test example that we did was a convoluted example. If I have to sort of do some introspection, the reason it was convoluted is because I forced you to think in a particular way. What I wanted you to appreciate was what we are looking into are these categories of deaths, right? So these are the number of deaths: 3,000 to 4,000, 4,000 to 5,000, and so on. The question then I was asking is, if these are my categories and these are the frequencies of what you observe, this will sum up to 48, this will sum up to 48. What is the overall difference? Okay, and is that statistically significantly different or not? Okay, for that we required chi-square. Okay, is that part clear? Okay. The question then we asked is 5.7 low, high, medium, and we tested this in R by running chi-square. You can write this very simple code. We got a p-value of 0.33. What is this p-value again? The p-value is the probability of observing 5.7, anything which is greater than 5.7. Extreme as 5.7. What is the probability? And the reason I'm going in this direction, so make sure that you understand why am I going in this direction, because I want to ensure that the value differences that I get, if I go in the other direction, if I go in this direction, right, if I measure this area, I'm not interested in lower values. The reason why am I not interested in the lower values? Why should I go only in this direction to measure the area? I can go in the other direction as well, right? So no, it's possible. So it's yeah, it's 0 and let's say infinity. Okay, I'm saying that the p-value is only this. This is your z. Why is it not this? This is also as extreme, right? Yeah. Okay, very, very good answer. Does everyone understand what Gautam said? So you're asking a very simple question that what is the probability of observing something as extreme? This being your test statistic where you're observing the differences between observed and expected. You want this to be more and more higher to quantify what would happen if the null hypothesis was true. What is the chance that you would have seen something as extreme, right? Your observations would have been very different from, you want it to be, you want to calculate the probability of this being very, very different from your expectation. That's in a way what you're trying to quantify. So is that clear? Why am I going in this direction? Yeah. Okay, good question. So what do you think? Okay, why? Why should it be? So let's say if this is your 0.5 mark, you're saying it should be this. Okay, so if it is decreasing on this side, what does this quantify if this value is decreasing? In this case, so don't forget your test statistic. So if it goes towards 0, right, you're saying that the difference between them is diminishing. They are more similar. Whereas here you're asking this question, what is the probability of seeing them to be as different as you have seen right now? At least as different as what you've seen right now. If you go low, then you're changing what you're testing for. The question that you're testing for is what is the probability that you see them to be at least as different as what you're observing. Okay. And we'll flip this example in just a bit and see the other extreme as well. Everyone with me? Everyone, this is clear? Yeah. Exactly. Yes, we'll do that. That's exactly what we'll do. It can only be positive. You just focus on the right side. But if it had been something which could have been on both sides, you would have measured both the sides. Okay. It's very clear. Is it very clear? This needs to be very clear before we proceed. Any questions? Yes. Sure. So what you're testing for is, I'll just draw it here. Don't see a duster. Okay. Which side? Okay, thank you. So this is also like this is a tutorial lesson for you to why you should choose the right example to talk with. Because if you choose the wrong example, which is slightly convoluted, it just takes more time to explain. Okay. I want to know if A and B follow the same distribution. I quantify this using some chi-square statistic, which is essentially measuring, this is your expected, so EXP, this is your observed. In a way, I want to quantify how different is observed from the expected. I want it to be really, really different, right? It could go here, it could be very, very small. It could also go and be in the opposite direction. That I don't care about. I want to just quantify this. Okay. So then I quantify this and I assume that that's your chi-square statistic. So the chi-square is a sum of square of random variable of normal random variables. So it's always going to be 0 to whatever infinity. Okay. Now the question that I'm asking is, what is the question? I'm asking what is it is at least as extreme. Why? Because I want this to be different. That's the question that I'm asking. Okay? So that's why I'm going to go in this direction, because I know in this direction is where the probability of seeing, I want to see at least this much difference. If I go in the other direction, the difference is going to go down. Okay? Does that make sense? So if this is your observed chi-squared statistic, if you move in this direction, the summation of that difference is going to go down as you move towards the left. Okay? What I want to see is if they did come from the same distribution, what is the chance that I would see something which is at least as extreme? Does that make sense? Any questions? Anyone else? Any questions? So this lens is required. This is not like a recipe. It won't work in all cases, and we'll see an example in which this exactly will not work. So please, if you have any questions, please ask now. Gautam, question? Okay. Okay, so we did an example, and we find you'll get the code, you'll see what happens, you'll run these experiments on your own, and you'll figure out, you'll get a feeling of what is really going on. Okay. One other test that we started to talk about was G-test, which is also called the likelihood ratio test. It's defined as 2 sigma OI. ln is natural log OI by EI. So there's one important thing that I wanted to focus on, which I did not talk about earlier, is this condition. Sigma OI is equal to the average number or the total number of observations is equal in observed and expected cases. So going back here, we satisfied that criteria. Okay, this sums up to 48. This sums up to 48. So I did not explicitly talk about it. Something that you should keep in mind, because I'll show you an example where I'm going to flip the question a bit and try to see what happens. Everyone with me so far? This assumption is required for your chi-square, Pearson's chi-square test as well. I did not explicitly state it. Why? Why is the assumption required? So what you're essentially testing for is you're testing whether the expectation, whatever your expected frequency is that similar or not. So if these observations, if the total number changes, then that assumption is what is going to break. So when we are comparing these things, what we are saying is, this is your expected model, right? What this is deciding is the relative version between category 1 or bin 1, bin 2, bin 3. What the question that you're asking is, does this look similar or not? Rather than how height it is. I could have multiplied this value by 10, and then the p-value would still be would have been 1, because I'm getting exactly the same distribution, but just the counts are scaled up. Okay? I'm looking for the difference in distributions, not in the absolute quantities. Okay. So we can do a G test also, and the G test. So this comes to some one question that was asked here, that if I flip the test, will the p-value change? The p-value does change, but more or less the trend that you get. So the p-value is 0.59 here, still greater than 0.5. We got a p-value in your Pearson's chi-square test to be 0.33. This is the p-value of G test, still different, but still above 0.05. Okay, so we still fail to reject the null. Okay, now let's flip the question a bit. So now the question that I'm asking you, this is just 2019 to 2023 data. This is again the same frequency, everything is same. We're just focusing on one version. And the question that I'm asking is, this observation that we made in April 3524, is it a rare or is it an extreme observation? Or is it something that you would have expected anyway? How would you solve this? And what is your null hypothesis in this case? The question that I'm asking is very, very clear. Is this a rare event? What is the probability of observing something as extreme as 3524 deaths? How would you solve this? Or how would you attack this? Okay. Okay. Okay, getting warmer. Okay. Anyone wants to add anything? The person at the back. The question is this observation that you're making, is this a rare event? Or would you be able to predict this by chance, based on all the observations that you have on your screen there? Or in other words, what is the probability of observing something as extreme as 3524 deaths, given the rest of the observation? What's your name? Priyansh. Okay, wow, that's a very straightforward conclusion. How did you come at that? Okay. Okay. Why Gaussian? Is it true for deaths? Okay, but good, very good attempt. Okay. Anyone wants to add anything? Yes, yes.
Perhaps how I would like to answer that way, understanding how we do outlier detection to get a good prediction. So if the way to get to an outlier through this predictive method was to be developed by training on this outlier detection, through experience we know that including outlier would give us a skewed process of getting there.
Okay.
And hence,
so how would you do? Let's assume this is an outlier detection problem. Yeah, it can be formulated as an outlier detection problem. So what kind of quantities will you calculate?
Perhaps I don't know how to do that yet, but what I'm just trying to get at is, if my predictive method is accurate, it probably does not involve the outlier in the data set. And hence, if I have a method of answering that question, if that method is correct, I probably don't have the outlier in the data set. Is what I'm trying to get at.
Okay, fair enough. Okay. Anyone wants to add anything else?
And hence, it won't be easy to get to that.
Okay. 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 Yeah, Shada. Okay, using chi-square, how? So hold on. So the question that I'm asking is, forget about the previous problem. Forget about you had data from 2019 to 23. If I gave you a plot like this, and you were to tell me whether whatever you're observing, is it within this observation, does it make sense or not? It's a slightly convoluted question, and you'll not get kind of this kind of question. But this is just to motivate you to think in a particular direction. We don't have any expectations. We don't have any expectations in this case. Yeah. Yeah, fair enough. That's a fair. Yeah, that's you can talk about it. Yes, you can. But do you want to focus on the question that I'm asking? Hmm. 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 Good. And we want some way to quantify that gap. Okay. So what would be the hypothesis? Okay. Anyone else? Yeah. Okay. Hmm. Yes, you could do that. That's a good way to do it. So I'm.
Did he say repeat those gaps and hence make it like did he say make the same gap somewhere again?
No, he's saying consecutive gaps between the observations. Okay. So I'm going to force you to think in a particular direction, is to think probabilistically. So all these methods are actually valid methods, right? You can quantify how different an observation is, what is an outlier, all valid. These are all valid ways to look at the data. But just for the sake of, you know, uh, for this class, let's try to think it probabilistically. What is the chance that something like that would happen? Huh, yeah. Okay, yeah, that's a valid way. Yeah, so you can calculate the mean, you can calculate the standard deviation, which is what I'm going to do. But I'm going to do it in a very sort of fashion, which I'll explain in just a bit why I think about it like this, right? So these are counts, and the moment you see counts, all the count models, the discrete models that we talk about, they come to mind, right? So you can model this as a Poisson random variable. You can also model this as a Gaussian random variable, which Priyansh Priyansh said. Those are all valid models, right? There's no right or wrong. I mean, we'll think about what is right or wrong in a couple of classes. What is the right model for this? But for now, we can assume that Poisson works, right? The question that I'm going to ask, and I'm going to just switch back to the slide again. Okay, so assume that this is a Poisson model, right? So you can figure out what is the Poisson mean. You'll figure out what is a lambda. The question that I'm asking is, what is the probability of observing something as extreme as this rare event? Now you have one more point of knowledge, which is this is a Poisson. You know its mean characteristic, and hence you know its variance. What would you do now? So I'm going to force you to think that this is Poisson. It can be anything. It can be a Gaussian also. The question is not more about the model. The question is about how do you formulate this mathematically or probabilistically. Okay, it'll be just the PDF. Okay, so let's forget about Poisson. Okay, let's forget about whatever it is. Okay, so if you fit any, doesn't matter what you fit, you will fit something like this, right? Everyone agrees? This is just the frequency distribution. Okay, what is the probability of observing something as extreme as this? So you said PDF. CDF, okay. What is CDF? Does everyone see why? So this is not a trick question. This is just to think about what does the extreme in this case mean, right? The extreme, the reason I picked this up was because this is a very small quantity, and I want to figure out what is, if I have a model for this data, how do I assess what is the probability with which I can observe it? Fair? Question is clear? Okay. So you can fit anything that you want, but if you were to go ahead and look for, if you were to fit a Poisson and you were to figure out what does this look like, this probability is going to be very, very small. Okay. What that essentially means is we are going to fail, or we are going to reject the null hypothesis. The null hypothesis in this case would have been what? What is the null hypothesis? I did not state it. It's not a rare event, which means that it belongs to this distribution, which means that whatever value that you calculate, it's going to have some significance that it came from this distribution. But this is a very small value, which means that it did not come from this distribution. Any questions? The test is a very simple test, which is what he said, which is I'm just calculating the probability of observing less p less than equal to x. I'm just calculating the probability of observing something like this. The test statistic is the assumption of the distribution itself. That's your test statistic. You can assume the distribution itself as the test distribution in this case. So this is a very contrived example. You will not have a realization where you get only one sample, but the way it would get realized in real world setting is you will have this data coming from different states, for example, right? So you will learn the distribution on one or few different states and then come back and test what is the value of, what is the probability of observing something as extreme given your other observation. So this is a contrived example. You know, this is something that you will not generally come across in real life because this is n equal to 1. So that's why this is just there to motivate you about how to think about what is an extreme event. Yes. Anything.
Is it right to say if I were to fit it in a way such that probability of observing that event is high, I would lose the probability of guessing the other, like the other part of the distribution?
Yeah, that's fair, right? So what the essentially what your question you're asking is that I'm using this point also to sort of figure out what that distribution is. Is that valid? So the short answer is that's not valid. In this case, I should have taken this data set multiple different times. Like I should have taken different samples and then come back and ask this question. But otherwise, I chose this question to sort of motivate how we look at it. So in its current form, it's not the right way to do things because you're actually using that point to figure out the parameters. But in general settings, when you come across this problem, you will have other data points to figure out what that distribution is. Mm-hmm. So in outlier, what you're doing is essentially very similar, except that you're not thinking about it probabilistically. What you're doing is you're saying that if I take the mean and the standard deviation, which sort of said here, how different is it from the mean and the standard deviation? Does it lie in that range or not? And the reason those tests work is because they are also implicitly making certain assumption that my outlier should, if something does not come into plus minus 2 standard deviations of my mean or median, that's going to be an outlier. So there is a probabilistic assumption that is underlying all these things. So that's what I wanted you to appreciate, right? So this is how you think about probabilistically. What is your outlier detection really trying to do? That's what it's trying to do. Everyone with me? Okay. Okay, so let's flip this question a bit, and the reason to do this example is because I sped through this analysis. Right? I sped through this analysis. I forced you to think in a particular way, but let's try to fix it. So one way to fix this would be that we have data across. We can figure out in 2019 and 2020 we have month-wise data. This is Jan to December. These are the different number of deaths. So a total of 88,000 deaths happened because of trauma in 2019. A total of 72,000 deaths happened in 2020. So if you look at this number, you will say that, okay, the deaths did decrease in 2020. What the question, however, I'm asking is, did the distribution change? That distribution here is defined based on the 12 months worth of data. So if you have, we had 3 categories to begin with, now we have 12 categories. The reason we had 3 or 5 categories early on is because I had determined or predetermined the range of deaths. That was my bin, that was my category. That's probably not the right and the most correct way to do that kind of analysis. I forced you to think it in that way. It's also not wrong to do it. One question, however, you would want to ask is, if I just take 2 years worth of data, just because we want to limit the number of data points we have 12 points. These are your 12 bins. The question that I'm asking is the death different across the two states? Is the distribution of deaths different across the 2 years? Question is clear? Across the 12 months. Okay. Okay. So the way to solve this is, because it breaks that assumption, right? The number of deaths that we have, they're not equal. If they're not equal, your standard assumption of chi-square, which I had not focused on early on, which is this does not apply. We did not explicitly check this in the previous iteration because we were looking at similar number of data points, which was 48, and those were the number of, if you sum up these columns in the previous example, those would have sum up to 48. They don't here because we are looking at a slightly different problem. So to solve this, you'll have to come up with a expectation. That expectation it's possible to arrive at that expectation using data from 2019. So if I take these values, if I sum them up and I divide them by the total sum, which is 88,463, this is the expected frequency of deaths that I'm expecting based on the data from 2019. This is your expected probability. You can multiply it now by the total deaths that you observed in 2020 to come up with your expected estimates. Is it clear what am I doing? Any questions? The reason I'm doing this is because I'm interested to again still understand, if I looked at the relative distribution of deaths across the 12 months, did that differ between 2019 and 2020? If these deaths added up to the same thing, everything would have been fine. They don't. So I come up with a revised estimate of, given I have seen this data, what is the relative number of deaths that happen in Jan, Feb, March, April up to December. So this relative deaths, which is PI, will sum up to 1. So, yeah. Sorry. Yeah, they have the same distribution. So this PI is not equal, right? This PI among themselves are not equal, but assumption I'm doing is, if I calculated the PI for 2020, are those similar between each other? Okay. It is immune to scaling. It is immune to scaling because you divide it by the expected counts on the bottom. You're squaring in the numerator, so you're sort of quantifying, you're over quantifying the small values, but it is under the assumption that those values are small to begin with. Again, because your null is true. So your null assumes that they are similarly distributed. So OI, so we'll do this example in just a bit. OI is expected under the null to be EI plus delta, which is a very small value. So that's why squaring it, that chi-square assumption holds. You are again assuming under the null. If this breaks, which is when you get high values, that's actually a good thing, because it says that that null assumption that you started with does not really hold. So those things add up. Does that make sense? Yes. Hmm. Hmm. If you scale all the values of if you scale all the values by 2, both observed and expected, yes, but the chi-square will get multiplied by 2. The chi-square value will change because the magnitude of effect that is coming, that you're getting, that you're over quantifying, right? By default, you have said that whatever is the difference, I'm going to observe 2 times that difference, right? So that is going to change based on that. Okay. Yes. So yeah, ideally you would not want to scale, right? Because that's not what your observations are. Your observations And this will happen when in any sort of test for that matter, right? So even if I take a z test, which is a z square, and if I multiply that the normal values by 2, we'll see an example of what happens if you multiply something by 2 in a normal case. The variance is going to inflate, right? So it's something that will happen with any normal distribution. So for example, let's just see this, right? So let's say this is your what happens if I multiply this value by 2? What will the curve look like? Let's just draw it here. Taller. Okay, who said taller? Okay. Any other taller as in? So this taller? Not good at drawing. So okay, why that?
It is getting 2 times. So this is y.
So this is PDF. This is PDF. Slow down.
So then what did
Okay.
you mean by?
I think maybe you are on the right track. Do you want to explain that reasoning again? So if this was X here, this what it is PDF.
Okay.
Why is PDF?
Because I made a mistake. If I did this, then the area would have been also. So we need to scale it down.
Okay. You want to use a different chalk?
I have not.
Okay, but you want to try? Anyone else wants to try? Flatten the spread. Okay, so this way. Yeah, 0 is same. Yeah, sorry. I mean, again, be forgiving when I draw. Please be forgiving when I draw. This is 0 is same. Yes, 0 is same. Is this correct? So, okay, go back. Thank you. So, when you do this, right, when you multiply something, any random variable by 2 or 3 or whatever that x is, what is happening is the mean obviously will scale. In this case, nothing happens. What happens to variance is it scales by a factor of, take a guess, yeah, 4, right? We'll see in just a bit why that happens. Okay, I have a slide. Hopefully, we can reach there. Does that answer your question? Yes. Huh. Yeah, the scaling won't affect in that case. You can take the frequencies, but the assumption when you're doing the chi-square test is on the observed minus the expected, right? So the observation, if you bring both of them down to 0 to 1, then you're actually scaling everything down. So you're going to negatively affect your p-value, which is you're going to get very large p-values then, right? Because I observed a count of 10 and now I'm saying that, that value is 0.1 after normalization. So that is going to negatively affect. Let's do this as an example in your assignment so that it becomes clear, okay? Thank you for that question. I think that's a good question. Any other questions? Very, very good questions, okay? Good. Okay, so so you'll do this example. Let's do this example in your assignment and you'll get a flavor of what happens if you scale something. And hopefully before, if you can just stay 5 to 10 minutes beyond 12:30 so that I can finish that part, because that will become important if you have to really realize what is really going on. Okay, so how is the G test related to chi-squared? So I had actually this is a place where I had technically stopped last time. So we are actually starting our lecture now. How do we do this? How do we solve it? Why do we need 2 tests? So we can start with this assumption that the observed values that you're seeing is just delta, right? So epsilon delta, if you've done calculus 101 or whatever that course is called now, or any other form of calculus, you've seen epsilon delta in some sense, right? So this is a small value, okay? So what I'm going to do now is replace this quantity. This is sigma I, and I'll try to write sigma different from my E. Okay? What do I do next? Good. Who said? Okay. What is the expansion? Can you help me with it? No one. Okay. Cube, you mean? Cube. So I'll just write this as delta cube. Everyone understands this notation? O of delta cube. That means it's the order of delta cube. So delta cube is going to be very, very small. Okay, what do I do next? I'll continue here. What is this equal to? So there is 2 everywhere outside and there is sigma outside. I'm ignoring all that. So I can take this inside. What next? Is it correct? Is it correct? Okay, what does this reduce to? Plus some delta cube. Does everyone see what is it going to be then now? Okay, louder. Okay, what do I do next? So sigma is missing here and 2 is missing here. Okay, hold on. Yes, good point. There's one point which is missing here. So you assume your sigma OI is equal to sigma EI. And by definition, what that would mean is your sigma delta I is 0. Okay, want to revise? You want to revise what you said? Can I write it like this? Okay. So it's very messy. Don't worry about it. I just want you to get the gist of it. It's there on the slides. Okay. So you can reduce. So it's there on the slide. Don't worry about it. So you can reduce the distribution to be the G test to be similar to be a chi-square test. People prefer just using G test for reasons we'll not be able to get to in this class. You can use chi-square test for all practical reasons. Any questions? Okay. Okay. Then comes our central limit theorem. So the central limit theorem, we're going to change gears now. So we have done one version of how to test for different distributions. Now we'll now see central limit theorem. Central limit theorem is a beautiful theorem. It says that you take any observation, it can follow any distribution in the world, doesn't matter. If I take multiple different observations from it, which are IID, which means that they are identical and independently distributed. Everyone understands IID? Identical and independently distributed. Okay, so it's not there in the slides. If you take the sum of the values of independent realizations of that random variable, which is your x bar, and you take a mean of that, which is x bar, then the expectation of this mean value, so this is mean of the mean, is equal to mu, assume, and your variance of this mean is equal to sigma square by n, then this quantity, which is x bar minus mu, so very powerful theorem. No assumption, minimal assumptions required. Again, this is in limit. Again, I will do my very loose math, but this is when n tending to infinity, this distribution starts to become a normal distribution. Okay, everyone with me so far? We'll not prove it, we'll take this at its face value. Okay, so you know something now, right? And if you have been sort of noticing these figures, which I've posted multiple times, you would start to make sense. You would start to sort of draw these analogies that they look very similar, right? They look very similar in that fashion. Can we prove it? Can we prove that this can be collapsed into this particular distribution using the central limit theorem? So this is your binomial, which has its mean as n theta, variance as n theta times 1 minus theta. This is your normal, which has its mean to be mu and variance to be sigma square. So two parameters for each of them. We want to say whether we can collapse one of the distribution to the other one. How would we do that? Yeah. Okay. You've seen this version? Okay, good. In any class or by yourself? 3 to 5. Oh, see, it's a okay, fair enough, right? So if you're done a probability statistics course, this is one of the theorems that are, or this is one of the derivations that you will do. You want to just flush out what you want to say? Okay. Okay, so this part is going to be slightly tricky, so don't get discouraged. You know, it's slightly tricky to get it right. So let's assume your this is Bernoulli of, let's say, some parameter theta. Bernoulli is either 0 or 1. Parameter theta is 1 theta, right? How can I make a Bernoulli into a binomial? Sum, right? So if I take a sum of this, let's call it whatever xn, this becomes a binomial. What do I do next? You've also seen this? You've also seen this? You want to try? No? Okay. You want to try? Sure. So what can I write about how can I leverage the thing that we just discussed? Sum of yi's, will it be normal? Okay, what is, revise it. So CLT says it's the mean which is going to be normally distributed. So I think you want to say, is this what you want to say? What should I write here? Which is? Okay, and what is that sigma square? Okay, what is this equal to? If yi is a Bernoulli random variable, what is sum of IID Bernoulli random variables? What is it equal to? N. N. Okay, yn. No parameter. What is the variance of yi? Variance of yi. This you have seen in the class. You can refer to class slides. What is the expectation of Bernoulli? What is variance? Right. This we saw, right? We saw this in variance. We also we saw this at the face value when we did the MLE estimation. Also, you saw some version of it. Okay. Now, can you tell me what this will be equal to? Does everyone see why? Or no? So this is actually a theorem, which is, so there'll be some back and forth. So when you sum up IID random variables, the expectation of the sum of the random variables is equal to sum of the expectations. Okay, that's a theorem, that's a lemma. You take it however you want to take it. That's also very easy to see, right? These are independent, so no sort of observation is going to come into play here. So xi, it's any random variable for that matter. How is expectation defined? So expectation is just the value times its probability summed over all possible realizations of it, right? So E of x is equal to sigma x times P of x. X is the observation, P of x is the probability of observing it. If you take the expectation of the sum, it will be equal to sum of the expectations. What about variance? So variance is defined as expectation of, so just better to write it here. You have again seen this, and this will right now appear a bit abstract, but you'll see in just a bit why we need all of this, right? So this is what is the expectation of your random variable subtracted by the mean. That's what your variance is. It's nothing fancy, right? You've seen this version. You've seen this version multiple times, basically. This is what the variance is. This will be 1 by n. In mathematical terms, for any random variable, this is when you have a sample, so you define the variance. This is if you have a random variable, you write it like this. Everyone with me so far? Okay. So the property that we're going to use is variance of sum of IID random variables. They have to be independent. Actually, that's the key here. It's equal to sum of the variances. If they are not, then life becomes complicated. We'll not do that as part of this course. Okay, everyone with me so far? So this equation, that is the first number, equation number 2 there, you can expand this a bit. And if you expand this, one of the properties that you can use, so you can just take the square of everything, and that becomes your a minus b square. Once you take the expectation, that can go inside, right? So in equation number 3, there are 3 variables. All of those are random variables. You can get inside. So I just want to explain one thing. So if you're getting confused, if you're getting impatient, just bear with me for 5 more minutes. Okay, so this very easy, a minus b square. You would have heard a speech talking about a plus b square. If you listen to news, where does the 2ab come from? Okay, what do I do next? So I can always take the expectation inside, right? So this is sum of 3 random variables. Okay, now see this. So this is a random variable. This is a constant. You know this is a constant. This is a random variable. This is a constant. E of x is equal to mu. That's what we start with. Expectation of the random variable is equal to the mean. What should I write this as? Expectation of a constant is constant. Expectation of constant times a random variable. Take the constant out. You get mu times mu minus 2 mu square. That's how you get the final value. Okay. Okay. Now you know this, right? Okay. So if you were to go back to this Bernoulli to binomial example, and I think I did a mistake of erasing it. But if yi is again Bernoulli, can you help me with what is the distribution of this quantity? Let me first write it in this format and then we will. So this by CLT is n 0, 1. What is mu here? Mu is, okay, and what is sigma? Louder. Okay, does everyone see that what we did? So we're just using CLT to do this. And if you take the binomial to be a sum of these Bernoullis, this is what your yn is. You can make it collapse into the standard normal. Okay, so that's how your binomial goes on to describe. So here I use theta, here I use p. That's basically, and I think I should switch this. I'll fix this q to be 1 minus p. That's basically 1 minus p. P, theta, they are the same. Okay, and q is just 1 minus p, which is 1 minus theta in that case. Okay, which is what we wrote here. Any questions? Okay. Okay, so this will be an exercise for you now because we are towards the end, which is to calculate the mean and the variance of the binomial random variable. And if you don't do this exercise, you'll see one version of it in your assignment. So that's what will be the exercise. Any questions? Okay, so very, very quickly, one digression because I did not talk about t-test, which I wanted to cover. So there's a recent paper that came out which says that we need to redefine the paradigm of how obesity is defined. So obesity, you know, there are these numbers, magic numbers of BMI. If you are between BMI, which is your body mass index, if it is between 25 to 29.9, you're overweight. If you're 30 and over, you're obese, right? The problem, however, with this particular one metric as a measure of obesity is it does not actually reflect what can go wrong in your body despite you not having enough mass or enough weight. So it does not actually establish that this one metric is not a good measure of what is happening in your body. You can start to develop organ failures despite not having a very high BMI. Okay? So this was a problematic metric, just like this is like literally 2 days old. The paper in Lancet talks about being able to fix this, which is to come up with the different traditional means. So I think there's, one second, there is 2 images overlapped here. So the problem with the traditional diagnosis of obesity is it does not, since it's based on the BMI value, it's not going to capture if you're technically overweight, but you also have excess body fat. This is, your previous notation would say that you're under diagnosis of obesity. The only reason you would sort of be, or you will be underdiagnosed in the sense because you have excess body fat and you are overweight, but you're not still being called, you don't have symptoms, but in the sense, this technically should be obese because you have excess body fat and you're overweight. Because you're not showing symptoms, it will be underdiagnosed. This people, what this will lead to is people who have excess body fat, they're not, they do not always have that magic number of 30. So they will sort of just be tagged as, they're not obese and everything is fine. But this is an under diagnosis in the sense that they should be technically called as obese just because they actually have excess body fat. You can have a less BMI because your body mass comes from two sort of muscles, like you have muscle strength or your muscle mass, and you have body fat mass. So you can have a lower number despite having an excess body fat, right? Because not all of it is contributing to your final body weight. And similarly with other metrics, you can sort of, even if you're obese but you actually don't have excess body mass, you don't have excess body fat, excuse me, and you're also not really showing symptoms, you would still be called obese just because you have that BMI number to be very, very high, right? So that's also problematic because technically, people can have a high BMI just because of their strength, just because of maybe their bone strength is higher, maybe their overall weight is higher, but they don't have any other symptoms. So they're just being overdiagnosed as being obese. And the other two scenarios are technically all obese. Some of the obese people will show some symptoms, some of them will not show symptoms. So this is problematic. The paper talks about being able to not only take one metric, which was BMI. The reason this was taken as a metric to diagnose obesity is because it's very simple. You take the weight, you take the height, and you're done. What this paper is proposing is that we need a more refined measure to be able to measure whether a person is obese or not. And the reason and the way it is going to do is it's going to explicitly measure muscle mass and trying to check whether you have any symptoms of obesity or not. So whether you have excess body fat, if you are, for example, if your normal BMI is 28.8 and you have excess body fat, but your muscle mass is normal and you don't show any symptoms, you will, in your previous analysis, in your previous diagnosis, you would be called overweight, but technically now you're preclinically obese. The reason because you have excess fat mass, which is not necessarily captured in your body mass index, right? So this is just to give you a preview of what we are going to talk about in the next class now, which is if you had measured BMI across two different populations, across let's say male and female, how do you measure whether these are similar or not? So this is the version of that plot which we have been drawing for multiple times, which explicitly spells out the hypothesis that we are going to test, which is the mean of the two populations similar or is it dissimilar? So we'll continue with this exercise in the next class. If you have any questions, I'll stick around. Please come and talk to me. Your assignment will not include a t-test, but it will include everything that we have talked so far. Okay? Thank you.